All right, I'm going to try something a little bit different in this video. Rather than this being like a polished lecture where I've looked at the notes already, like I said before, I've taught this course before, but I haven't used these exact notes. So while I work through the notes from this spring, I'm just going to record myself and we'll see if this is worth using in the future. This note is on properties of vectors, and let's just work through some examples and work through these notes. First of all, can I prove that all 17-year-old Canadians love rap music? And apparently there are about 30 million people who meet that criteria. So that's going to be a little difficult. How can we investigate this? Well, we can look at specific examples. So Joel is 17 and Canadian. Joel loves rap music. Is this enough to prove? No, it's only one specific case out of 30 million. What if we had 100 examples? If I found 100 kids that liked rap, is that enough? No, that's still not enough. How can I prove it for all? That's a lot more difficult. It's a lot harder. All we have to do is find a single counter example. So if I can find one case where this is not true, I've already proven that not all 30 plus million 17-year-old Canadians love rap music. So as a counterexample, let's say we find Betty. She is also 17 and Canadian. Betty does not love rap music. This single counterexample instantly disproves what we are trying to prove. So this can be hard to prove something, but if we can find a single counterexample, this is enough to disprove. So this is sufficient. So it can be hard to prove general cases, because if we find a single counterexample, then we cannot prove it. It's no longer valid. All right, let's talk about proving some stuff related to vectors. Can I prove that vector addition is always commutative? And we're going to be working in two different spheres here. We're going to be working in R2, or 2 space, or 3-dimensional space. And we're going to be working in R3, or 3 space, and that is 3-dimensional space. And we're trying to prove if if vector addition is commutative. We have talked about this briefly before, but basically that means we're trying to say, is it true that vector A plus vector B is equal to vector B plus vector A? And we've also talked briefly before about commutative, that idea of commuting. So you can imagine you live in London and work in Toronto, and so you go back and forth. And if it takes 2 hours each way, doesn't matter if you go to London and then back to Toronto, or Toronto and then back to London, it's still going to take 4 hours. It's still going to be the same result either way. All right, let's look at some specific examples. Let's take our example vector A, where the vector A is in R3. 1, 2, 3 are the coordinates to define it. So we're working with an algebraic or Cartesian vector here. We also have our vector B, which is 0, 2, and 1. And let's add them together. Vector A plus vector B. Remember, we're just going to add up the individual coordinates. So add up the x values. 1 plus 0 is 1. Add up the y values. 2 plus 2 is 4. Add up the z values. 3 plus 1 is 4. Let's try going in the opposite direction. B plus A. We're going to kind of work in the opposite way. So we'll take a look at these values first and then these values. So 0 plus 1 is 1. 2 plus 2 is 4. And 1 plus 3 is also 4. So are these the same? Yes. Hooray. but this is not sufficient to prove. Not sufficient proof. Although it's not a counterexample. It doesn't prove it wrong. It does work. So it shows that this may be true. All right, we need to prove this for all. And in order to do that, rather than using a specific vector or specific vectors, we're going to have to use some general vectors. So let's describe what we're going to do, and then let's do it. So we're going to set up generic vectors. So let's have some vector A at A1, comma A2, comma A3. So that's the X, Y, and Z value. So we're working in R3. And vector B. So B1, B2, and B3. Let's take a work on our left side here. Vector A plus vector B equals A1 plus B1, comma, A2 plus B2, comma, A3 plus B3. Let's take a look at our left side. Or sorry, right side. So let's try going the other way. A squared plus B squared, or sorry, vector A plus vector B. So B1 plus A1, comma, B2 plus A2, comma, B3 plus A3. And this is equivalent to A1 plus B1, comma, A2 plus B2, comma, A3 plus B3, because we know the addition of integers, like just working with plain numbers, is commutative. And these are equivalent, so this is all going to be the same. And so, actually, sorry, I made a mistake here. Let's take a quick step back. The difference was we flipped it around. So, B squared plus A squared. That's what we just did here. So we flipped the order. We saw that they're equivalent because addition itself is commutative. And so this one right here and this one right here are the same. And so we can say that addition is commutative, because this is equal to vector A plus vector B. So vector B plus vector A is equal to vector A plus vector B. So therefore, we have proven that vector addition is commutative in 3 space, or like I just say R3 normally. All right, cool. Let's continue. Is the dot product commutative? So that is A dot B equal to B dot A? And remember, with the dot product, it's basically a test to prove if our two vectors are orthogonal or at 90 degrees or right angles to each other. And that happens when our dot product is equal to 0. Let's take a look at a specific example. So this does not prove, however, it does show if it is possible. So let's define our vectors. Let vector A be 1, comma 2, and we're just working in 2 space this time. And let vector B be equal to -3, comma 4. And let's try finding our dot product. So then we're going to test A dot B. And remember, we're just going to multiply our x values and our y values, or our A1 and B1, and then our A2 and our B2. So let's do that. A1 is 1 times -3 plus our 2 values, 2 times 4, is going to give me -3 plus 8, or is going to give me 5. Now, Let's try our next example. Let's do b dot a. And we're just going to switch the order. So I'm going to do my b1 value, which is -3, my a1 value, which is 1, plus my b2 value, which is 4, and my a2 value, which is 2. And we're going to have -3 plus 8. And look at that. That also equals 5. So this is encouraging, but it is not sufficient proof. Not sufficient for all. It only shows that it works for this specific example. So once again, let's define some general vectors. So we'll let a be equal to ax and ay. So the x component, or the x coordinate of a and the y coordinate of a in our ordered pair. And similarly for b, that'll be bx and by. Let's try this again. So let's do a dot b equals, so ax bx, ax times bx, plus ay times by. And now let's try the other direction, b dot a. So bx times ax, plus by. All right, let's try it the other way. Now, oops. Now, b dot a. So we're going to have bx times ax plus by times ay. And those are going to be equivalent because multiplication of numbers is commutative. 2 times 3 is 3 times 2. So same idea here. So this is the same as ax bx plus ay by. So it's the same as a dot b, because in general, multiplication is commutative. If you take some more advanced algebra, you can define rules where it's not commutative, but in our everyday math, it is. So don't worry about that. Just know that that's some crazy stuff that you might see in university. And therefore, we have proved that dot product is commutative in R2 or 2 space. All right, cool. Let's investigate cross product. Is cross product going to be commutative? So, in other words, is A cross B, or the cross product of A and B, equal to B cross A? Let's take a look at a specific example. We'll define our vectors. Let A be 1, 2, 3. So we're in R3 or 3 space. And we'll have our vector B as 1 and 0 and -1. Let's find the cross product. A cross B. And we can use the Miss Spring method here. So let's list our coordinates. 1, 2, 3, 1, 2, 3, and 1, 0, -1, 1, 0, -1. Let's chop and divide it up. And let's crisscross. So my values are going to be -2 -0, and 3 minus -1, so +1, and 0 -2. Or in other words, -2, 4, -2. And we can write that over here. So -2, 4, -2. And now let's flip the positions of our vectors. So instead of doing A cross B, we're going to do B cross A. So let's rewrite this. So I'm going to have 1, 0, -1, 1, 0, -1, and 1, 2, 3. 1, 2, 3. Let's chop. And then divide it up. And let's calculate. So 0 times 3 is 0, minus 2 times -1 is -2, so +2, comma, -1 times 1 is -1, minus 3 times 1 is 3, comma, comma, 1 times 2 is 2, and 1 times 0 is 0. So let's see what we get. We're going to get 2 and -4 and 2. So B cross A is equal to 2, -4, and 2. Are these values the same? No. Not the same. So this means that A cross B is not equal to B cross A. And we can describe that a little bit. Therefore, we have disproven let's write this a slightly different way. So we're not wrong. I'm just going to rephrase it. We have proven that the cross product is not commutative using a counterexample. So we only need one case where it's not true to prove that the general case is not true.